Dr. Muthu Gnanamani received his master's and PhD in chemistry from the University of Madras in Chennai, India in 2001 and 2007, where he worked on microporous and mesoporous supported hydrotreating catalysts. He joined our group in 2007, and he's been working feverishly as a postdoc ever since. His presentation is entitled Low Temperature Water Gas Ship Reactions over Alkali-Promoted Cobalt Carbide Catalysts.
Thanks, Gary. Good evening to all of you. I think Professor Darayos took me all the time, so I just, before going to the presentation, I must say thanks to the organizer, Gary and Uschi, for giving the opportunity to present my work here. And I would like to congratulate Burt for the award. So today I'm going to talk about the alkali-metal promoted cobalt carbide catalyst for low temperature water gas shift. I just briefly go for the water gas shift and importance of the water gas shift reactions in the petroleum industry and the catalyst that has been used for the water gas shift. And we are going to see the transition metal carbides and the significance in the water gas shift, especially the molybdenum carbide. And of course, my talk is on cobalt carbide for water gas shift and the promotional effect on the alkali group on metals like lithium, sodium, potassium, aluminum, cesium, ore. And we're going to see the effect on the potassium loading as well. And finally, we can make some conclusions based on the study. As we all know, that the water gas shift is a conversion of the same gas, water making hydrogen for producing the hydrogen, so that hydrogen can be utilized for the ammonia synthesis. It has been well known in the industry for making the ammonia synthesis. And recently, the fuel cell process for making fuel cell processing also this water gas shift has been very important on this aspect. So the industry, there are two different catalysts being used today, the high temperature shift and the low temperature shift. In the high temperature shift, the iron and the chromium based catalysts have been used, and in the 8% of 80 to 90% of iron and the chromium 8 to 10% with the stabilizers like the copper, aluminum and the other alkalis. The typical condition for the high temperature shift like the 320 to 450 degrees temperature, 10 to 60 bars. And in the case of steam forming at high temperature, the CO inlet will be at 12 to 40% on a high basis, and the CO exit, the CO comes out from the high temperature shift reactor will be like 3 to 5%. And the product mixture that goes to the low temperature shift is like a 3 to 5% on the CO concentration basis. And the typical catalyst that is used for low temperature shift is a copper, zinc, aluminum based catalyst. And you have stabilizers like silica, chromium, and manganese also been tried. Finally, what the CO comes out from the low temperature shift is as well as 0.3% on a high basis. So what actually the present catalyst, the disadvantage or the limitations of the present low temperature water gas shift catalyst is the low volumetric activity, means you need a large catalyst bed in order to reach the equilibrium CO conversion. And the second thing is like the catalyst centering, particularly if you operate on a catalyst at high temperature. And irreversible deactivation when you get exposed to liquid water, like when you are shutting down the reactors at the time, or by accidentally the water formation is there, liquid water formation that deactivates the copper, like the copper is oxidizing into copper nucleus. So another thing is like the sensitivity of the poisons, low-level poisons, especially that presence in the syngas, comes along with the syngas like the sulfur and the HCl, so that need to be removed before processing that. So these are the limitations of the present water gas shift. So in order to boost that, or in order to looking for the alternative water gas shift catalyst, the Pat Hampson workers, they actually published a work recently on the tire molecular carbide catalyst, and they shown that the higher activity compared to the copper zinc under standard conditions, and there is some degree that the catalyst shown sulfur tolerance compared to the copper zinc and the catalyst. And the Moon and the workers, they actually published the work on molecular carbide, and they have shown that the molecular carbide is not stable for a longer period of time, and it could deactivate by the presence of water. So, and again, the Nagayan workers, they are also shown that when you add a cobalt, you can stabilize the molecular carbide to some extent, and you can increase the low temperature water gas activity of the molecular carbide. So, not to do so, then I can just look at the Nagayan co-workers. What they did was they actually put the molybdenum, the cobalt into molybdenum like a 50-50%, and we tested the water gas activity and the conversion. As you see, the conversion looks comparatively stable compared to the pure molybdenum carbide, and it is comparable with the commercial copper zinc catalyst. When you don't have any cobalt in it, and the catalyst being deactivated is almost by 50%, whereas in the case of cobalt added catalyst is shown steady activity, but there is some initial deactivation. It seems that the molybdenum carbide, if you promote it with the cobalt, it is showing a reasonable activity, and it is comparable with the present catalyst. And the one advantage of this molybdenum carbide is also a sulfur tolerance. So we look for the active phase of this molybdenum carbide and cobalt molybdenum carbide, and the Nagai, they propose that the cobalt molybdenum carbide is stable and is stable towards the water gas shift activity. So the increase in activity, they're proposing that likely due to the increase in the carbon deficient side and the cobalt atoms of the cobalt molybdenum carbide. So what we actually use is we try to prepare the cobalt carbides and promoting with alkali in order to increase the water gas shift activity of the carbide, and see how that's stable under the water gas shift conditions. And we did an XRD analysis of both fresh and spin catalyst after being activated with 1% organic helium and being characterized. And we are trying to see if there is any phase changes that occurs during the run. And then we did this reaction in a fixed bed tube-led reactor, and finally compared the activity stability of the catalyst. So we prepared this catalyst by impregnating the alkali nitrates by incipient redness and fibrillation, and having the atomic ratios in the range of 100 cobalt to 5 alkali metals. And after impregnation, we just dried it, and then usual calcination at 6 hours. Before doing the run, we did a carburation in situ using a CO at 5 to 3K for 52 hours. And this is the typical reactor we use for conducting the moderation run, and the mixtures will be passed through the steam generator so that it picks up the water.
Use your finger.
So the mixture like hydrogen, CO, and nitrogen and helium mixtures will be passed through the steam in order to pick up those steams generated from the pump, and then it gets passed through the reactor, and the water will be condensed at the trap, and the residue, the gas was passed through the GC, and we are analyzing those gas components of CO and the CO2 using the GC like the solid. So the typical catalyst loading will be like 1 gram of the promoted oxide catalyst, and in the case of copper, zinc, aluminum, we tested for a comparison purpose, we took 0.2 gram of catalyst and diluted with the powder gas in 60 to 80 micron size. And so as I said, the activation will be done in situ using the CO at 5 to 3 K for 52 hours. And the typical conditions for the water gas shift that we followed is the P-gas conversion, like it is typical for the fuel processor condition in terms of the CO2, and of course we did this reaction at atmospheric pressure. We vary the temperature from 453 to 573 K with 300 degrees Celsius, and the components being analyzed C1CH4 CO2 using the SRI GC. It contains both silica gel and molecular zinc column. The detectors will be like TCD and the FID, and in order to boost the CO2 detection, we have that mechanism to boost the detection of CO2. And we did an elemental analysis on fresh catalyst after carburation. The carbon content of the catalyst, as you see, as we go down from the group, like from lithium to cesium, the carbon content increases, and the values in the bracket shows like it is based on the values in the bracket shows the theoretical weight percent of carbon on the basis of the cobalt carbide contains the formula of CO2C. So the carbon content was calculated based on this formula, and you can see that value keeps dropping is because of the increasing the atomic weight of the alkalis. So in the prepared catalyst, as you see that the values keep increasing. The carbon content is keep increasing as we go down, as we move down the group. So it means that the carburation is affected by the presence of alkali, and the amount of carbon deposited, the amount of carbon we are getting from the catalyst, fresh catalyst is higher than, is increasing with from lithium to cesium. So the method that we use for the elemental analysis, as we have the instrument we use for variant ES analyzer and the CHM analyzer to analyze the carbon content. And the fresh and used catalyst will be dissolved in a spectrum with nitric acid mixture, and the emission spectrum of dissolved species were compared to those of the standard solution. The XRD analysis we did on the fresh passive catalyst, and as you can see that we are having a dominant peak of the presence of the cobalt carbide at 42.52 eta, and we have an additional peak that indicates the presence of the carbon, especially the cesium and rhodium and potassium promoted catalyst. So it means you have indication that the presence of the additional carbon that covers the cobalt carbide surface. And we will see that how that affects the water gas shift activity. So we did the effect of temperature on the water gas shift of the catalyst, and we are comparing here the temperature effect on the lithium. For example, here the lithium shows a much lower activity even if you increase the temperature from 450 to 550. And sodium and potassium exhibit higher activity compared to the other promoted catalysts. We are in the next slide. I will show that the unpromoted one, and here we are comparing the effect of the alkali And so rubidium and cesium again is dropping, but could be because of the accumulated surface carbon could influence this activity difference. And so here we are comparing the effect of potassium loading, and as you see that the cobalt carbide here is the square one shows the cobalt carbide, and the potassium promoted tablet showing the higher activity compared to this one. The effect of loading is clearly indicates that potassium is influencing the water acid activity by promoting the carbide formation. And here, I'm trying to compare the fresh and the used catalyst. And what we did was, once we complete the run, and we calculated the catalyst and trying to take for the solid. And what we have seen here is the phase changes, as we clearly seen here. When we have the no alkali, and you can see the clear change in the phase from carbide to metallic character. It is not clearly completely metal, but it has contains some carbon as well. So, but it mostly contains metal as well as the carbon. So, when you started with the carbon, it's going to a metallic phase under this condition. Whereas this lithium, sodium and potassium, you have that phase. You have the carbide phase still after the end of the run, and whereas the rubidium and cesium, again, you are losing the carbide phase and going to a metallic phase. And of course, that metal phase is the SCT phase we are getting. So what it observes is that the phase transition from carbide to metal was observed on all other promoted catalysts except sodium and potassium. Means sodium and potassium retains in the carbide phase under the present condition. That could be the reason why we have seen that the activities are much higher compared to the other promoted catalysts. And we are trying to plot the weight % of carbon that in the used catalyst with the water acid rate that has been observed at the temperature, constant temperature. And none means we have the low potassium, and with the lithium, sodium, and potassium, rubidium and cesium. When you see that you have the typical curve that correlates the weight % of carbon with the water acid rate, it means a linear correlation. You can see that as we increase the weight % of carbon, the water acid rate also increases with the alkali series. So sodium and potassium dominates over the other alkali metals. And in order to confirm further the effect of potassium in this case, what we did was taken the cobalt carbide, run it the water gas shift under certain condition, and then we discontinued water gas shift and we did a hydrogen treatment. And as you see, after the hydrogen treatment at 240 for 24 hours, the water gas shift activity dropped, and then it stays constant, so it means, whereas in the case of potassium, the activity dropped and then it keeps increasing with the time. It means it could be because of the carbon could builds up as the run progresses, and it makes again the carbon phase by the promotion effect of the potassium. So this indirectly indicates that the cobalt carbide could be stabilized in the presence of potassium under the water gas shift condition that ultimately increases your water gas shift activity. So potassium is essential for the cobalt carbide for the low temperature water gas shift applications. And finally, we are comparing the long-term stability of the catalyst with the various alkali metals, and as you see that the water gas shift activity is dropped for cobalt, lithium, and sodium. Also has shown some deactivation, but it's really comparable with the potassium. Although the potassium is shown a higher activity, and it was quite stable for close to 40 to 50 hours of run. So potassium promoted exhibits higher and the most stable water activity from metal and metals. And of course, we have seen this effect on rubidium as well as cesium, but I am not showing here. But rubidium and cesium also show the similar deactivation behavior. And we are comparing this activity of the catalyst, potassium promoter catalyst, with the other people who published. So based on molybdenum carbide catalyst, for example, in the case of molybdenum carbide, the reaction rate has been is 0.306, and it is comparable with our present work like potassium promoted cobalt carbide catalyst. So whereas if you compare this activity with the commercial catalyst is almost half of that activity. So still the potassium promoted cobalt carbide catalyst is not as a commercial catalyst, but it is showing some promising activity for a longer period of time. So with this actually I would like to just say that the future work that we are going to do on comparing those surface compositions of the carbide along with the water gas shift activity. Why? Because the molybdenum carbide, as the people who did the work, they are finding that the cobalt oxy carbide is more active than the regular carbide catalyst. But in this case, with just a study, we could say that whether it is just because of the carbide is active or is it oxy carbide. But we are trying to do with the XPS to measure the oxygen to carbon ratio in order to see if there is any changes with the alkali. And when I showed these results to Gary, and he was telling that he has seen that alkali effect like sodium and potassium on a platinum celia catalyst. I guess platinum celia, is it?
Platinum. Well, first it was platinum zirconia, and Honda found that in their combinatorial.
Yeah. And so he has shown that there is a trend of, the sodium and potassium behaved differently than the other alkalis, and the water gas shift rate was compared with the formate decomposition. It helps decompose the formate much quicker than the other alkalis. So we are trying to see if that works on this carbide catalyst by doing the in situ drip cobalt carbide and alkali promoted cobalt carbide catalyst for the future work in order to see what's going on the surface. And this I would like to conclude. The cobalt carbide seems to be active for the water gas shift, the rotor-based water gas shift conditions. And the origin of this activation of deactivation of the cobalt carbide is primarily due to the phase transition from cobalt to metal to the carbide phase. Carbide to the metal phase, and sodium and potassium promoted exhibits higher activity compared to the other alkali promoted catalysts. And the results being confirmed by the XRD that the sodium and potassium retains the carbide phase during the water gas shift. And finally, we are making a comparison between the percentage of carbon content the spin catalyst with the water gas shift phase we observed, and we have seen that linear correlation in the existing catalyst. And finally, I'd like to thank all our group members from Clean Fuels and Chemicals group, and I would like to thank Common Means of Kentucky for financial support. And thank you for all for listening.